Good afternoon and good evening to everyone joining today's Lubrizol 360 webinar entitled Going Beyond Base Oil to Deliver Optimal Thermal Performance and Safety in Immersion-Cooled EV Batteries. Next slide, thank you. Just a few housekeeping matters before we begin. My name is Suki Ubi and I'm a Market Insights Manager here at Lubrizol. Microphones and cameras are disabled for attendees. However, we do welcome your questions and comments at any time in the chat. We'll pick up as many as we can in the Q&A after the presentation. This webinar is being recorded. Webinar materials will be emailed to attendees after today's session. Next slide, please. And now a note from legal. This webinar is being presented by the Lubrizol Corporation for the purpose of providing information and insight into the markets and applications into which its products are used. Certain attendees of this webinar may be competitors of each other. Please be advised that this webinar will be conducted in strict compliance with antitrust and competition laws. Competitively sensitive subjects such as prices, discounts, and terms of sale and other examples listed on this slide may not be discussed. This webinar may be terminated immediately in the event of improper discussion. I hope we can avoid that. Next slide, please. Our speakers today are Tom Corrigan and Andy Richenderfer. Tom is a Technology Development Manager for Battery Thermal Management Fluids. His PhD in Organic Chemistry from Ohio State University focused on the design, synthesis, and applications of new chemistries. In his role at Lubrizol, Tom's expertise helps us to understand thermal transfer in electric devices and the molecules and formulations that enable it. Tom works closely with Andy Richenderfer, a senior research engineer in the Strategic Research Group at Lubrizol. Andy's PhD in nuclear science and engineering from MIT first took him to the Knowles Atomic Power Laboratory, where he was a thermal hydraulic engineer. He later joined Lubrizol to work on thermal management strategic projects. Next slide, please. Okay, so Tom and Andy have kindly agreed to talk us through some of their research and discuss new developments in thermal battery management. And with that, I'll hand it over to Tom and Andy.
Thank you, Saki, for that introduction. I'm Tom Corrigan, joined here today by Andy Richenderfer, and we're really excited to share with you the next generation cooling options for battery electric vehicles. So in today's webinar, we will walk you through Lubrizol's formulated approach to immersion thermal management fluids. But first, I want to start with the basics, right? So we're here to talk about immersion cooling. What is immersion cooling? And so I'll use a little analogy, right? So imagine you're on vacation somewhere warm. You wake up in the morning, you go out for a run, you come back, you're overheated, hot, sweaty, you want to cool off as fast as possible. How are you going to do that? You might be thinking to yourself, well, I'm going to go jump in the pool. And if that was your answer, that is probably the most efficient thing that you can do to cool off in as quickly as possible. So when we talk about immersion cooling for battery electric vehicles or for batteries, it's essentially the same concept. So what do? We take the battery pack or the module and we completely submerge it into a cooling fluid. And so what this does is it maximizes the contact area of the thermal transfer fluid with the battery cells themselves, including all of the electrical connectors, and rapidly removes and can manage the heat generated within a battery pack. So when we're talking about fluids for battery cooling, it can't just be a pool of water, right? Electronics and conductive water aren't going to play nicely. So there's a lot of things that have to go into consideration for developing an immersion cooling fluid for battery systems. It has to be dielectric. It has to have a high dielectric breakdown. It has to have good thermal properties, right? When we talk about thermal properties, we really think of viscosity, specific heat capacity, thermal conductivity, and density. In addition to these things, it has to be compatible with the rest of the materials in the system. So this is, very critical as we go forward designing systems that can implement immersion cooling for battery electric vehicles. So immersion cooling is really a next generation cooling technology that can enable maximized efficiency and safety. And we'll walk you through some of the data that proves that out during the course of this presentation. So if we jump to the next slide, though, before we dig into some of the specifics on immersion cooling and specifically Lubrizol's formulated approach to immersion cooling, I want to briefly cover the other methods that are used to cool batteries in electric vehicles today. So the most simple and straightforward is an air cooling system, right? So in this case, you've got a blower or a fan that forces air as your cooling medium through the battery pack. So again, this is the most simple. This is, if we go back to the run analogy, would be the equivalent of walking into an unair conditioned hotel room after your run and sitting in front of a fan until you cool off. So it will work, but it's going to take more time, and you're going to be very much limited by the ambient temperature of the air that's being pushed through the system. Getting a little bit more sophisticated, we have our indirect cooling methods. So this can be refrigerant cooling or an indirect water glycol type cooling system. So in both of these systems, we have a cooling fluid that's piped through a cold plate that can reduce the temperature of the cold plate and then conductively withdraw the thermal energy from your battery pack. So refrigerant cooling typically uses a refrigerant in a two-phase system, so it uses evaporative cooling to cool the cold plate. It has some limitations in that it typically uses fluorinated types of chemistries, which are known to have poor global warming impacts, as well as it's limited by the ability to only cool but not heat, because you can't use a refrigerant to warm the battery if you're in a cold environment. The water glycol systems are efficient, but again, the indirect nature of it, the fact that it's removed from covering the entire surface area of the cell and the thermal resistances associated through the pack material as well as the cold plate, leaves some performance to be desired within this system. So we move into the immersion cooling system again, which is what we're focused on today. And so if we jump to the next slide, we can talk a little bit about the formulations, right? So I mentioned those four parameters: your viscosity, specific heat capacity, thermal conductivity, and density. Of those four parameters, viscosity is by far the biggest lever that we have to pull in terms of optimizing the thermal transfer coefficients for these fluids, where the lower the viscosity, the more efficient the fluid is going to be at removing heat from a system. Now, that sounds like we just want to move towards the lowest viscosity fluid that we can find. But we need to keep in mind that there's other things to be considered, such as those material compatibility as well as safety. So viscosity and flash point of a fluid typically trend in the same direction. So those are very much directly correlated. The lower the viscosity of your fluid typically means the lower the molecular weight of the individual constituents, which means the higher volatility, which means a lower flash point. And so if we look at this graph here, you can really see two distinct trend lines. One for the pure hydrocarbon-based fluids, so things that are just carbon and hydrogen, and then one a little bit above that. And those types of fluids are typically a little bit more polar. They contain oxygen. So rather than pure hydrocarbons, they might have some ester in them as well. And looking at this chart, you see, okay, well, if we go to an ester system, we can maintain that low viscosity and also boost our flash point. So that's really attractive from a performance and a safety perspective. But then there's that third consideration of material compatibility. So pure ester systems often have poor material compatibility due to their polar nature with things like elastomeric seals and other polymers within the system. On the surface, it seems like a simple solution. We dunk the battery in a dielectric fluid and call it a day. But really, this is just starting to show that there's a lot of other considerations that can go into optimizing the different characteristics of the fluid across performance, safety, and material compatibility. So if we jump to the next slide, we can address some of the performance issues right here. So again, talking about using a formulated fluid versus a standard base oil, which you might see used for immersion cooling. It could be, a Group 3 refinery fluid. It could be a synthetic like a PAO. In this case, we're comparing a PaO2 fluid versus one of Lubrizol's Evogen thermal management fluids. So the PaO2 is the blue trace, and the Lubrizol fluid is the green trace. And so it's really difficult to have a conversation about electric vehicles without talking about charge time. And so what we did is we put these fluids into a very representative system. Andy will talk about some of the details of that in a few slides. But in short, it's a 12-cell module using prismatic cells with 50 amp hour current. And then we ran it through a variety of performance and safety testing. And so this was a fast charge test. And so you can imagine that your electric vehicle system has some safety electronics installed where if your battery hits a certain temperature, it will start to derate. And so that's what we did here. We ran a different charging sweep, and we found that with the PaO, let's say that your derate threshold is 43 degrees Celsius. So you can hit a 3C charge rate. That's a 20-minute charge. With using that PaO2 as an immersion cooling fluid in your battery module. If we use the formulated fluid, we don't hit that 43 degrees Celsius until we get out to about a 3.4C charge rate. So in terms of what that means to a consumer, that's 2.5 minutes less, or a little bit over 10% quicker charge time versus a PaO2. So the performance, again, can be very much validated with the data that we can show through this fast charge testing. And if we jump to the next slide. So material compatibility, again, coming back to that is critical. So one of the main reasons that we still see the indirect water glycol systems being predominant in the industry is due to their familiarity within the industry. So the automotive manufacturers or OEMs have been using indirect water glycol cooling systems to cool internal combustion engines for decades now. So they're very comfortable with it. They know how to plumb it, how to pump it. And when we start talking about switching to an immersion system, these types of fluids have different physical properties. So we're moving from aqueous fluids to hydrocarbon or organic-based systems. So there's a lot of unknowns in terms of the compatibility with all sorts of different materials, from your conductive metals to your epoxy resins to your elastomers, your seals, the other polymers, the hose materials. And so we've taken all these things into consideration, and we've set up a lab that does some extensive material compatibility testing with many of the common types of materials that you would see going into the builds of these vehicles. So you'll notice from the data in the table on the right, not everything is extremely compatible. So there are some things that need to be swapped out. So we work diligently with customers, OEMs, to identify the appropriate materials so that we can avoid issues down the line that might arise from material compatibility issues. That said, things like aluminum, copper, stainless steel, our Lubrizol fluids have excellent compatibility with these types of conductive metals, or metals that might be used for housing or other physical containment of the fluid itself. And part of that is due to the inherent properties of the fluid, and another part of that is due to the additives that Lubrizol has formulated to improve things like corrosion and oxidation resistance. So if we jump to the next slide. Andy will walk us through a little bit of the thermal performance data that we've collected in our module.
Sure, thanks, Tom. So I'm going to go through some of the abuse and performance testing that we've performed on our prismatic battery test module. Can you go to the next slide, please? So this is the representative test module that we used. It's about 12 prismatic cells, 50 amp hour cells in a 2P6S format, with about 1.5 millimeter spacing between the cells. So the cooling path flows the fluid across the bus bar, in between the cell faces, across the opposite bus bar, and then out the module. So as Tom alluded, the immersion cooling really maximizes the area of heat transfer, in addition to lowering the number of layers that the heat has to go through in order to remove the heat. And that's really what separates it from the indirect water glycol type cooling. So for this type of module, it takes about 1.2 liters of fluid in order to fill the whole thing. You can also see that there are 2 burst discs, one on the top and one in the rear, and that's in case of thermal runaway. You go to the next slide, please. So for the performance testing, we ran numerous tests, and we're only showing the results from one of them here. This is a 3.5C fast charge with what we called a hot start. A hot start is where the entire system started at 40 Celsius. And this would be representative of, if your car was sitting out in a hot parking lot, empty of charge, and you needed to charge it right away. How would that system perform in that type of scenario? So in the graph on the left, we have 3 curves. The red curve with the dashed line is the charge rate. So you can see, it starts at a flat 3.5C charge and then goes through a US06 drive cycle. The green and the blue curves, the solid green and the dotted blue, you can see show the maximum temperature of the hottest cell in the pack at any given moment. And so you can see, this is where we start to differentiate against the base oils. You can see the PaO2 reaches 54, almost 55 Celsius, but then the Evogen TM1100 fluid reaches 2 to 3 degrees below that. And so that's where we recoup some of that charge time that Tom was talking about earlier by enabling a faster charge and keeping the cells at the exact same temperature. Now, in addition to the maximum temperature, there's also the issue of cell temperature uniformity. In these types of packs, the battery that will age the quickest is the one that is the hottest. And so you could do a good job of cooling one cell, but if you don't cool them all uniformly, you'll artificially age your pack much more rapidly. So in this case, what we're showing again is the PaO2 in the blue, the Paratherm LR in the orange, and then the Evogen TM1100 in the green. And so you can see that the Evogen TM1100 cools the pack the most uniformly, and usually about a 9-degree delta between the cells, whereas the base oil, the PaO2, reaches almost 12 degrees. So again, what this means is that with the Evogen TM1100, not only are you cooling your cells better overall, you're also cooling them more uniformly, and that's going to extend the lifetime of the pack, and that again is value brought to the customer. Next slide, please. So the next thing we're going to talk about is abuse testing. This has significant impacts to safety. I think we're all well aware of some of the issues that electric vehicles have in regards to battery thermal runaway. And what this really covers is the propagation of that thermal runaway from one cell to the next. Oftentimes in these types of tests, you must assume that one cell goes into thermal runaway for one reason or another, and it's on the onus of the OEM as well as the tier 1 suppliers to demonstrate that you can protect against this thermal runaway and give the passengers enough time to exit the vehicle safely. Next slide, please. So we executed this test by a nail penetration. So what that is that a metal bar penetrates the module and goes about halfway through the first cell. This initiates that thermal runaway event in the initial cell. And then the goal here is to see just how good some of these immersion coolants are in preventing thermal runaway. And the way it would do that is by providing sufficient thermal heat transfer away from that first cell to prevent any of that excess heat generated by the gases developed during the thermal runaway event from spreading to the second, the third, the fourth, and the other cells in the pack. So in this graph, you're looking at the 3 separate fluids in the top, middle, and bottom. And then in each graph, you see 3 curves. So there's the gas curve, the fluid inlet, and the fluid outlet. The gas is a thermocouple that is located just above the module, just above one of those burst discs. And what this measures is as the gas develops and releases from one of the cells going into thermal runaway, it'll be captured by this thermocouple. And that gas is usually released at a very, very hot temperature, 400 Celsius and above, really. So it's a very good indicator of when one of these cells has actually entered into thermal runaway. So if you look at the PaO2 base oil, you can actually see each of the 12 spikes that occur meaning each of the 12 cells went into thermal runaway at one point during the test. It's actually very, very clear. Now, if you look at the two Lubrizol fluids, both the Paratherm LR as well as the Evogen TM 1100, you can see that you only have that initial spike. Only that first cell, the one that was penetrated by the nail, actually went into thermal runaway. After that, there was no such event that occurred. So this is, pretty good indication that these fluids, as well as, the immersion cooling technology, was able to prevent the cascade of this thermal runaway from one cell to the next. Next slide, please. So if we dive in a little bit deeper, we're looking at the battery temperature of the first cell and the second cell. So on the left is the first cell, and what you can see is, again, that PaO2 base oil, the temperature skyrockets immediately, almost to 400 Celsius, and holds steady for quite some time. Now, for both the Paratherm LR and the Evogen TM 1100, you actually see a little bit of a delay. It's like 15 to 20 seconds. But this is an important aspect of what helps prevent that heat from distributing across the module so rapidly. It's that additional heat transfer that you're getting out of these high-performing fluids that is really ultimately preventing this propagation of thermal runaway. Now, if we go to the second cell, right, this is the one that really matters the most. The first cell we knew was going to go into thermal runaway. The second cell, that's the one where we have the question mark. So for the PaO2 base oil, you see that this one as well skyrockets to about 400 Celsius and holds steady. So a good indication that the heat from the first cell passed to the second cell and caused it to break down and enter into thermal runaway. For the Paratherm LR and the Evogen TM 1100, you can see that the maximum temperature the cell reached was about 100 Celsius, maybe just a little beneath that. This is crucial as, each of these cells, depending upon the chemistry and the cell type, things of that nature, have a maximum temperature threshold that they can reach before they go into thermal runaway. And what's key here is that both the Paratherm LR as well as the Evogen TM 1100 provided enough heat transfer to prevent that cell from entering into that temperature state, whatever that threshold is, to initiate the thermal runaway event. So another good indication of the performance of these two specific fluids and the differentiation they have against the base oil. Next slide, please. So a picture is worth 1,000 words. And I think these two are pretty clear. So you have the PaO2 base oil on the left, then the Evogen TM 1100 on the right. The left module is completely destroyed, essentially. And more than likely, this safety event would have probably propagated into the other modules within this hypothetical battery pack, excuse me. For the module on the right, so if you actually look closely, you can see little white tabs that exist at the top of those prismatic cells. Those tabs are each little tiny burst disks. And what will happen is when a cell enters thermal runaway and it develops that gas, those burst disks will pop. And so you can see in the cell on the left, that's the cell that was penetrated. Well, the burst disk popped. I think that's the one that we expected. But now you see the 11 other tabs still existing where they are, as they should be, because they didn't enter into thermal runaway. No gas was produced, and so no bursting event occurred. So another good example of how this fluid is preventing the battery thermal runaway, or the propagation of battery thermal runaway from one cell to the next. So I think that does it for me. Tom is going to talk a little bit more about the fluid properties and talk you through the products we have.
Yeah, thanks, Andy. I think that's an excellent job of covering not just that immersion cooling is the most efficient way to cool your system, but also the choice of fluid within immersion cooling is equally as important. So with that, here are three of Lubrizol's Evogen thermal management fluids that we've put together. So we have a TM 1070, TM 1100, and TM 1150. And you can look through the data table here and see that they primarily are differentiated based on their viscosity, and we formulated to a variety of different viscosities, more or less to meet flashpoint requirements for different applications or different end users. So we have, three kind of general packages that we've put together, but I also want to highlight that our formulated approach that uses, not a single base fluid, allows us to put together our base stocks in combinations that allow us to formulate really anywhere between or outside of these fluids. So if someone was, interested in a 200 flashpoint fluid, well, we absolutely already have that one, but we would be able to formulate to really any flashpoint or viscosity spec that might be of interest to a customer, and that makes us, really unique in this space, that we can not just offer discrete, quantized values, but we can really cover the entire spectrum of those. So this is just a flavor, a little taste of what sort of products we have to offer. And then if we move to the next slide, I want to touch just a little bit more on the additive package. So I mentioned it before, but I think this is another really key component to the immersion fluid that allows it to last for the lifetime of the vehicle, and really give you the maximum value for the fluid. And so, we use a variety of different additives. I think I mentioned, some corrosion protection, some antioxidancy. Another kind of unique one that we've incorporated is an anti-static additive. So this actually arose from an issue that a collaborator was having, where they were seeing static buildup within a system of a pumped fluid, due to the fact that the fluid was actually too dielectric. So we look down at the bottom here, we've got a chart that goes through different conductivity regimes. Starting on the far left, you have, things that are extremely insulating. So like your pure mineral oils, your synthetic PAOs. On the far right, you have a conductive fluid, something like tap water that has dissolved electrolytes in it. And so what we found was that if your fluid is actually too insulating, it can lead to this static buildup issue. And it was prevalent and very much noticeable because they were actually getting arcing of that static buildup across their connectors, and we're seeing pitting of the material. And so, they kind of put it back on us and say, hey, is there something you can do to resolve this issue? And so what we did is we developed an anti-static additive that we incorporate in a very small amount that just subtly boosts the electrical conductivity from the purely insulating regime in more towards the static dissipative regime. So we have the ability to, again, similar to viscosity and flashpoint, to formulate to really any conductivity on the spectrum by use of these additives. Now, obviously, we wouldn't want to go too conductive to the point where we could risk a short, but staying close to that insulating static dissipative border allowed us to boost the conductivity just enough that they could dissipate that static buildup, and we were successful in resolving that issue. So again, just another example of how the formulated approach really comes together to produce a superior fluid. And so if we jump to the next slide. So that's, essentially wraps up our webinar for today. And I hope that we were able to convey that immersion cooling really is the most efficient and safest form of cooling battery packs within electric vehicles. And also that the fluid choice is equally as important for both safety as well as performance. So the cooling options vary, and so do the results. We've showed today that our formulated fluids have been proven to be better than just your standard base oils. And the testing also shows the benefits under extreme conditions, like something like a nail penetration, which might be representative of some sort of impact on the road. So the fluid is efficient at preventing the propagation of thermal runaway, which is really critical for safety and the future of electric vehicles as a whole. So in closing, right, we can formulate a fluid that can be tailored to meet really just about any system need out there. So I will, thanks for joining. Andy and I are happy to address any questions that the audience might have.
Thanks again. That was really great, Tom and Andy. I see a couple of questions in the chat, so let's kick off with them. The first one is, how often must the oil be changed, and what does this depend on?
So based on our experience, right, so this is still, it's a new technology, but based on our experience, which is, goes back quite a ways in in automotive fluids, we anticipate this to be a fill for life fluid. So some of the main factors that typically degrade fluids, things like contamination due to combustion, high temperatures, wear particles. We don't have any of that in this system. So it's relatively mild conditions compared to what we see for some other quote fill for life fluids. So we fully anticipate this to be a factory fill for life fluid.
Excellent. Thanks for clarifying that. Another question. This one asks, what is the ideal DE breakdown voltage and to balance resistance and connectivity?
I'm going to say that's going to be fairly system dependent, which is, I know, not probably the complete answer that you want to hear, but dielectric breakdown, we target, I think the spec that I've seen in the industry is greater than 10. All of our fluids have dielectric breakdowns definitely over 30, probably closer to 60 kilovolts. We want to be well above any potential battery voltage that we might see, and with batteries approaching 1 kilovolt now, we definitely want to stay well above that. In terms of conductivity, again, it really is dependent. If you don't have any of the static buildup issues, the more insulating is probably going to be better. But again, anytime you have these moving insulated fluids, you have the potential to build up that static charge. So we would always recommend putting in a little bit of that anti-stat to mitigate it, but keeping it closer to the insulating static dissipative border there.
Okay. And a related question, are there any specific requirements for battery housing or the box containing the fluid?
I'll say that the only requirement is the material compatibility, right? So it needs to be compatible with the fluid. We've seen a lot of different people investigating different architectures for the housing materials. And there's been many or most of them have been successful. So there's no one way to do it. And it really comes down to the design engineers, as long as we're on the same page with material compatibility.
Okay, I'm jumping through some of the questions here. This one I think is a good one. Have you got any experience with aged fluids or the expected performance and how that will vary between fresh and aged fluids?
Yes, so that's a good question, and we do monitor the aging of the fluids. We've taken pre-test and post-test fluids and analyzed them for their various properties. I'll say that the primary thing that we're looking at, which is historically less studied, are the electrical properties, things like conductivity, and we will sometimes see subtle increases in conductivity, but really nothing that's been alarming. And typically we see a plateau, right? So when you first introduce it into the system, maybe it picks up some contaminants, the conductivity might rise just a tiny bit. Then we typically see it level off after that. So we have also fluids apart from just battery thermal management, but on deployed for cooling other electronics like computers, compute systems, servers, and similarly there, we do pull samples from real world applications on a monthly basis that we've been doing for a couple of years now, and we're monitoring these types of fluids, and yeah, we don't see any real degradation of the fluid. Okay,
that's great to hear. More questions. Can immersion cooling enable fast charge beyond 3.5 C? What are the limits?
I'm going to let Andy handle that one. The answer is definitely yes.
Okay. That was the short answer. So, Andy, give us the longer one.
Sure. So we've seen results. We've done testing at 6C. Very, very successfully. We also have some deployments in more motorsports type applications where you get short bursts into the hundreds of C. You can think about kinetic energy recovery systems during braking. So it can certainly enable much beyond 3.5 C. And we expect really what we're shooting for is in the 6 to 10 C range, to try and get fast charging down time-wise as quickly as possible.
Okay. Another question. They're coming thick and fast, which is a good sign, I guess. Is there any benefit or need to pump this dielectric fluid through the modules and then out to a radiator, or some method to cool the liquid to improve the cooling?
Yeah, Andy, I'll let you handle that one again.
Yeah. So yes, as the heat is transferred from the battery into the fluid, you would then want to cool the fluid. So yes, what is typically seen is some sort of forced convective system with a pump. However, the types of pumps and the radiator or heat exchanger needed are pretty common. So, like a centrifugal pump, probably a plate type heat exchanger. It's going to be dependent upon the customer's system, but we do have experience helping customers pick out those types of products. So whether you need assistance in sizing your pump or heat exchanger, or making sure that the pump housing and materials are compatible with the fluid, we do have quite a bit of experience in aiding our customers in that sense.
Excellent, good to hear. This one, I'll ask, but feel free to tell me when you're not allowed to go into the details. What types of esters are considered for immersion cooling? What are the main bottlenecks, if any?
Yeah, I mean, I won't comment on the details of the esters that we use in our formulations, but they're very widely, commonly available esters, and there are some considerations and bottlenecks. One is, well, the biggest one is probably the material compatibility. Like I mentioned, we would typically not ever recommend a 100% ester system due to the material compatibility issues. Another is sourcing of the esters and purity, right? Depending on the grade of ester that you get, you might have residual acid or some other contaminants from the raw materials that go into it, which can be, not great to have within your system. But yeah, in general, there are a number of esters that can work for this application, and those are, really the two things that we would consider when choosing.
Okie dokie. Is the static surface charge caused by the oil flow a problem, and how can it be prevented?
Right, so it is typically caused by the flowing of the dielectric material. And so you can have a static buildup, between two different components that might be separated by the oil. And so it can be prevented in a number of ways. And the way that we always like to see implemented is in engineering control, where essentially you have everything properly grounded within the engineered system. But should a ground fail, or should a ground not be in place, this is where our anti-static additive comes in. So our anti-static additive can help with that, dissipate that buildup of static charge, should the engineering controls, not be sufficient.
Excellent. And I think I'm going to just fit one more question in. Is there a need for low temperature pumping viscosity, and how would it best be characterized?
Andy?
Yep. So yeah, we do look at low temperature pumping, in the event that it's the dead of winter and you need to charge your car and get things going. So we primarily look at viscosity for that, but we do have internal pump testing in order to ascertain, just how good a performance you're going to get out of a pump in order to circulate the fluid. I think a lot of people like to assign pour point to that sort of metric. That can be good and bad at times. I think it's best used perhaps as sort of a general indicator of pumpability. But in reality, you should probably actually test it in the system at the low temperature to ensure that you're getting the pumping that you need. Often what we find is that the pour point specification is probably a little overly spec'd, so it's set for a little too cold, when in reality the fluid can circulate just fine, at like a -20, -30 Celsius, without much issue.
Okay, excellent. Well, thanks very much, and not just to Andy and Tom, but everyone attending today. And as mentioned, Lubrizol will follow up with links to the slides and additional information, including an opportunity to continue the conversation. This concludes the webinar. Thanks and goodbye.